Hello and welcome to 5 Minutes of Physics. Today we're going to be looking at June 2009, Paper 3, Question 3. It's an experimental one about nuclear physics. So, a teacher demonstrates how the count rate detected by a Geiger-Müller tube encounter depends on the separation of the front of the tube and the radioactive source. The source emits alpha particles only. Okay, very important, no betas or gammas. So we've got our Geiger-Müller tube that's connected to the counter, a separation, and the source. And you see it's one of the directional sources like the ones we used in class. Part A, measure the separation of the detector to the source. So this is where you're going to get out a ruler and actually measure it. Write the answer in there. Nice, easy, 1-mark question. Part B, before the source is in place, the teacher takes 3 readings of the background count rate in counts per minute. Calculate the average count rate in counts per minute. So average, we're going to do 28 plus 25 plus 28, and we're going to divide it by 3. So 28 plus 25 plus 28 is 81, divided by 3 is 27. That's the average in counts per minute. A student takes 3 further readings of the background count rate. State what is wrong with the student's data and suggest what might have caused this. So the student's data, we've got 29, 52 and 28, whereas before we had 28, 28 and 25. There's quite a nice glaring anomaly here in 52. So what's wrong with the student's data? Well, we've got an anomaly. That 52 is an anomalous reading, and suggest what might have caused this. So 52 is quite a lot larger than 28. It's almost double, in fact. So it's probable that the student, instead of doing the background count for 1 minute, has done it for 2. And that's a normal sort of error that could come up. Measuring for twice the amount of time, not resetting the stopwatch, is a common error. So that's what they'd be looking for there. Okay, so now we get the results from their experiment there. We've got a graph, count rate in counts per minute, so the count rate coming off the source, how far away they've moved that source from the detector. State the range in centimeters of these alpha particles. Well, their range is going to be how long it takes them to drop to 0, so it's going to be 6 centimeters there. Describe how you would use the apparatus to get these results. So this is a long question. This is a 5-mark question, and this is a method. So you need to make sure you have nice step-by-step answers. What are you going to do to find the range of alpha particles in air? Well, when you're doing an experiment, you always state which piece of apparatus you're using, what it's measuring, what you're writing down, and how you're changing things. And the first thing that you do, which they've already told you at the beginning, is you measure the background count rate using a Geiger counter. You could do that 3 times and find an average if you wanted to. Then what you're going to do is you're going to place your source in front of your Geiger-Müller detector a certain distance away. So you could start by saying with a separation of 0 centimeters. You're going to record the count for a minute, because it's count rate in minutes, and you're going to then vary that separation from 0 up to 8 centimeters. You could then repeat each of those centimeters 3 times and find an average, having removed any anomalous results. And if you want more detail than that, you could say that you're going to change the separation distance from 0 to 8 centimeters, changing it by 1 centimeter every time. A final thing that you could add, extra marks there, is you could say to get the count rate from the source, you need to always take away the background reading. So if our background reading was 28, and let's look at one of the examples, at 0 there was a reading of 2000, the actual reading of the source would be 2000 minus 28 instead, once you've taken away the background reading. And that's not so important for this experiment, but if you're finding half-life, really important, don't fall into the background radiation trap. Okay, finally, this question asks which one, in bold there, so only choose one, of the following is a sensible safety precaution in the experiment put across in a box. This is worth 1 mark, and these are normally quite friendly. So choice 1, performing the experiment in a dark room. Choice 2, placing the students behind a LED screen. B, switch off all fans. Or C, using tweezers to handle the radioactive source. So performing in a dark room, obviously a silly idea, just fall over stools that way. Switching off all the fans, well, I'm not sure how that would change anything at all, but I guess it would stop airflow. So rather than a safety precaution, it would stop the movement of air, which might absorb the alpha particles, so could arguably affect the experiment, but doesn't make it more safe. The 2 safety precautions here we have are placing the student behind a LED screen or using tweezers to handle the radioactive source. Always choose the obvious one, go for the tweezers. This is the one that you'd use most commonly for it. You probably wouldn't need to put students behind a LED screen because we're only using alpha particles. Alpha particles only have a range of 8 centimeters in air, so unless you have your students closer to the source than 8 centimeters, it's just sticking their hand in front of the source, it's not going to be a problem to them, and they're not going to be in any harm. Okay, explain why each to 3 is not a sensible safety precaution in this experiment. Well, we've gone through that. Performing the experiment in a dark room could be dangerous because you wouldn't be able to see which way the source was pointing. Part B, placing students behind a LED screen is unnecessary because the alpha particles have a very small range in air, so the radiation isn't going to reach the students. Switching off all the fans won't change the range of the alpha particles, and so won't make it more safe. Thank you very much for listening. Good luck with your revision. Remember, a little bit of revision every day goes a long way.